So, in this video, we'll discuss about diagonalizability. Okay. Simply recall that in the previous video, when we were proving the theorem that the geometric multiplicity of an eigenvalue is always less than equal to the algebraic multiplicity of the eigenvalue. Recall the proof technique. What did we do? We took an orthonormal basis of, so we took orthonormal basis, right? What was it? It was u1, u2 to uk. After assuming that the geometric multiplicity of lambda is k, we took an orthonormal basis for the null space of a minus lambda I. Okay, where A is the matrix we are interested in. Then what we did? Then we extended it to a basis in Fn. Okay, F can be R or C, Fn. So, I mean, we can take Cn to be a bit more secure. So what was so how did the basis look like? It will be u1, u2 up to uk, right? And then it will have uk plus 1 up to un, right? This need not be orthonormal, okay? But again, so let me call this uk plus 1 tri, right? So this need not be orthonormal, but again by Gram-Smith, you can make this orthonormal. That is u1 comma u2 up to un will be a orthonormal basis of Cn. Okay, now consider this matrix. So consider the matrix P whose first column is u1, second column is u2, and so on. The last column is un. So what is this? This is an n by n matrix. Okay. Since each column of P is linearly independent, the rank is full rank, hence P is invertible, right? So P is invertible. The second thing I want to note is that since P is orthonormal, or since P is orthogonal, what we can say is that, so what does it mean by orthogonality? We have PP transpose being same as I, right? This is the condition for real matrices. Okay, this is for real, or you can say for Rn. Okay? And for Cn, you have P times P star equals I. What is P star? P star is transpose conjugate, right? This is for Cn. Okay, but what does that mean? That means, so let's deal with Cn as of now. Okay, that means, that implies, or we can do with Rn also. This implies P inverse is P transpose, right? Now what can you say about, okay? So consider this matrix P transpose A P, right? What would this be? This would be equal to C. So this would be P transpose times A, and what is actually P? P is nothing but U1, U2, and so on. un. What does that mean? That means you have first row as a times u1, second column as a times u2, and the nth column as a times u1 un, right? Okay, but then uh, we know that u1 u2 up to uk, right, are eigenvectors corresponding to the eigenvalue lambda, right? What does that mean? That means you can write this as, instead of a u1, we can write lambda u1, lambda u2. Remember, these are columns, sir. So on up to lambda uk, and then after that you have many elements which we are not concerned about. Okay, so I'll just write, uh, dot dot dot. There are elements. Okay, I just write, but we are not worried about that. Okay. So what would this be? This would be so recall what is P transpose. In P transpose, the first row will be u1, the second row will be u2, and so on. The last row will be un, right? This is multiplied by lambda u1, lambda u2, lambda uk, and then you have many other elements. Okay, let me put the stars. Okay. Now this would imply you get a matrix. Observe closely that you will get a matrix where you'll have lambda times ik. Why ik? Because the first k rows we are considering. Okay, and here you'll have something star. Let's call it star, and here you'll have all zeros. Okay, here also some other star, right? Some matrix. Okay, star. Why does this hold? This holds because of orthonormality of u1 u2 up to un. Okay, this is why. Okay, now let's do one thing. Let's see one more thing. You can observe that uh, from here, okay, from here what we can see is that the eigenvalues of P transpose AP, right, are same as the eigenvalues of A, right? In fact, so what did we start with? We started with an eigenvalue of A, then we showed that it is implies lambda is an eigenvalue of P transpose AP. What is P? P is the matrix formed by the eigenvectors, right? Not precisely the eigenvectors, but you can say the eigenvectors extended, right? Extended to form a basis. Okay, so this is how we showed, right? Let's look at the definition of diagonalizability. So the definition says that A is said to be diagonalizable if uh, if A is similar, so A is similar to a diagonal matrix. Now, what do you mean by A is similar? So we will denote this by A is similar to some diagonal matrix. Okay. So what do you mean by asimilar? That means there exists an invertible matrix P, right, such that A can be written as P, or you can say uh, P inverse AP is equal to diagonal matrix, some diagonal matrix. Okay, which is same as saying, that AP equals to P times the diagonal matrix, right? So the very important result here is that suppose you take A to be in MNR, okay, and let's say uh, so suppose that S is some matrix for which S is some matrix such that S inverse AS, okay, this is equal to the diagonal matrix, diagonal with say D1, D2 up to Dn, okay, right? Then S has to be, right? So you can say the S has to be equal to, okay, S has to be equal to V1, V2, Vn, right? Where Vi or Vj is an eigenvector corresponding to the eigenvalue Dj of what? Of the matrix A. Okay. What does that mean? So, result. This is the result, right? How would you prove the result? That is also straightforward. So, the proof would be like this. So, what does this mean? This means, so from here you can say that AS will be equal to diagonal of, would be equal to S times diagonal of D1 up to Dn, right? Okay. So, let us say, suppose S is equal to some, say U1, U2 up to UN, some UNs, right? We do not know what they are. That what does that mean? That means on the left hand side you have AS, which will be A times U1, A times U2, so on up to A times UN, right? And what do you have on the right hand side? On the right hand side you have D1 times U1, D2 times U2, and so on up to Dn times UN, right? What does this mean? This means that A ui equals to di ui, right, for all I. What does that mean? That means, so this has two implications. First implication is that di is an eigenvalue of A. The second implicate with eigenvector ui, right? This is the implication. Right? This is exactly what we wanted to show. Now, additionally, from this result, we can observe that, right? So result, which is this is a corollary of it. So corollary of the previous one. You can observe that A is diagonalizable if and only if uh, A has n linearly independent eigenvectors. Okay, so if n, so this is an equivalent condition for diagonalisability. Okay, this is obvious, right? This is a corollary from the previous one, because if it is diagonalizable, so if it is diagonalizable, then we know that the diagonal entries of that diagonal matrix to which A is similar is precisely the eigenvalue with corresponding eigenvectors. That is what we show. Again, if A has n linear independent eigenvectors, then just form the matrix, right? Form a matrix P to be those n linearly independent eigenvectors, then P inverse AP will be equal to the diagonal matrix, right? One more thing we obtained is that, so we have also note that this is all the eigenvalues, right? So you can say that, so this sigma A, this is said to be the spectrum of A. What does it mean? It means the set of all eigenvalues. That is called the spectrum. So the spectrum of A is nothing but same as the spectrum of the diagonal matrix. That is same as T1, T2, Tn. Okay. Let's look at a few examples to clarify the idea. So, example. Look at this matrix 0, 1, 0, 0. Is this diagonalizable? Give it a try. Okay, let's see how to proceed. So definitely this is a, so if it is diagonalizable, okay, if it is diagonalizable, what does that mean? That means then A will be similar to, so let's call this A. A will be similar to what? A will be similar to the diagonal matrix, right? With what will be the eigenvalues? What will be the diagonal entries? The eigenvalues, right? But we know that the eigenvalues of A are zeros, two zeros. So this is 0, 0. But that implies that A is similar to the zero matrix, 2 by 2, right? What does that mean? That means that A can be written as sum P times zero matrix times P inverse. But then this would be nothing but the zero matrix, which is a contradiction. What does that mean? That means A is not diagonalizable. Okay. Look at the next example. Say for example, A is this matrix 2 1 1 0 2 1 0 0 2. Then is it diagonalizable? Again, let's say suppose it is diagonalizable. Suppose. So also observe that uh, 1 minute. So from here observe also that, see, why was it not diagonalizable? Because all eigenvalues were 0, right? So we can say that if A is nilpotent, what does that imply? That implies all eigenvalues are 0. What does that imply? That implies that A is not diagonalizable. In this case, suppose A is diagonalizable. Suppose A is diagonalizable. What does that mean? That means A can be written as S times a diagonal matrix. What will be the diagonal matrix? That has to be 2 to 2, right? Because they have to be the eigenvalues times S inverse, right? But what is this? This would be nothing but 2i3. Right? That means A is 2i3, which is a contradiction. So A is not diagonal. Okay. Now observe one more thing, that if we have a non-diagonal matrix, okay. So if A is not a diagonal matrix, and A has only one distinct eigenvalue, or you can say only one eigenvalue, then what does that imply? That implies that A is not diagonalizable. Okay, this is another observation we could conclude from the example. Okay.